How's it going, everyone? Mr. Geyser here with lesson 9 on inverse trigonometric functions. For today's lesson, we have 4 main skills and learning objectives to tackle. First, we want to understand and use inverse sine, cosine, and tangent functions. Second, we want to find the exact values of expressions involving that inverse sine, cosine, and tangent functions. Third, we want to use a calculator to evaluate inverse trigonometric functions. And finally, fourth, we want to find the exact values of composite functions with inverse trigonometric functions. Remember, I'm looking for you guys to recall from unit 2.8 that a function has an inverse function if and only if it has that 1-to-1 ratio. That is, it must pass that horizontal line test. In the images below, in figure 1, you'll be able to see that the sine function does not pass that 1-to-1 behavior. However, if we restrict the domain, such as in figure 2, to that interval where x is equal to and greater than negative pi over 2, but less than or equal to positive pi over 2, which corresponds to the interval between that minimum and that maximum value for one sine wave, now we have that 1-to-1 function. The inverse of the restricted sine function is called inverse sine function. There are 2 notations that are commonly used to denote the inverse sine. We can either say y is equal to sine to the power of negative 1x, and we wouldn't say it like that, but we'd write it like this, or we can write it as y equals arc sine of x. Both of which are exactly the same and commonly used to describe the inverse of sine. Also, the notation of y equals inverse sine of x has the same symbol as that inverse function notation for inverse function of x. The inverse sine function is denoted by inverse sine of x, is the inverse of the restricted sine function, where y is equal to sine of x, where x is greater than or equal to negative pi over 2, or less than or equal to positive pi over 2. Thus, y equals inverse sine of x really means x just equals sine of y, where we're just flipping where that x and y would commonly go. When y is between negative pi over 2 and positive pi over 2, and x is between negative 1 and positive 1, we have this 1-to-1 ratio for sine of x. We read this y equals inverse sine of x as y equals the inverse sine at x. In figure 3 below, it is graphically represented of this inverse sine. Notice that if we look at this first figure here, sine of x does not pass that horizontal line test. When we restrict it to that small interval between the minimum and maximum, we have this little small wave. This wave here, we're able to reflect across that y equals x line to create this inverse functions. We can explore these inverse functions today with our examples. But remember, we want to find the exact values of these inverse sine x. The exact values of inverse sine x can be found by thinking about inverse sine of x as an angle in that restricted interval between negative pi over 2 and positive pi over 2. So we're going to treat this inverse sine of x, that whole thing, as theta. We want to consider, for example, that inverse sine of 1/2 is equal to pi over 6. Since the answer is an angle, we can use theta in our process to find the exact values of that inverse. In that first step, we're letting that inverse sine of x be exactly equivalent to theta. We're then able to rewrite our inverse sine functions as sine of that theta is equal to x. That third and final step is to use the exact values in example 1 to find the values of theta in that interval between negative pi over 2 and positive pi over 2 that satisfies that sine of x equals, or sorry, sine of theta equals x. For example 1, remember that theta is equal to inverse sine x means that x is actually equal to just sine of theta, where x is in that interval between negative 1 and 1, and theta is in between that interval of negative pi over 2 to positive pi over 2. We want to complete the table of exact values for that restricted domain. For this table here, we just want to try and take this unit circle and identify where only these parts are of our sine graph, because this is where the domain of sine of x and the domain of inverse sine of x are both 1-to-1 ratios. First, I want you guys to see that negative pi over 2 is actually equivalent to 3 pi over 2 radians. This pi over 2 here has its corresponding negative pi over 2 right down at the bottom. So if we take that 3 pi over 2 and place it into our sine function here, it's exactly equivalent to negative pi over 2, which is just negative 1. And what we're really doing is grabbing this y value from this corresponding radian and filling in the table here. Once we've done that, we're really just identifying all of these y values here. We're able to now look at the domain and range of our inverse sine. Big important note though. Sine of theta is restricted between negative pi over 2 and positive pi over 2 because this is the only place where inverse sine and sine of theta have a 1-to-1 ratio for x and y, where y is really just theta. This is a unique interval for sine and inverse sine. A different interval would be valid for cosine. Let's look at sine first. In example 2 here, we want to use the information in our table above to find the exact values of these following. For part A, B, and C, what we're really wanting to try to solve is, what is that theta? If we set inverse sine of 1 equal to theta, we're now able to rewrite this equation in sine of theta is equal to positive 1. Well, really, I just need to look at where sine of theta is equal to 1 here, and it's equal to pi over 2. So I can say that theta is equal to pi over 2. But if I know that inverse sine of 1 is equal to theta, then inverse of sine of 1 is equal to pi over 2. Let's go through that same process here with part B. For inverse sine of negative 1/2, we just set this equal to theta. We set this equal to theta. We then want to rewrite this as a sine function of theta is equal to negative 1/2. Well, we find when our sine of theta is equal to 1/2, and it's going to be at pi over 6. So we can state that inverse sine of negative 1/2 is equal to theta, which is equal to negative pi over 6. Now, let's take a look at part C. Set the theta, rewrite that as a sine function, identify where that square root 2 of 2 is, and we're able to then find that inverse sine of root 2 over 2 is just equal to that theta, which is pi over 4. However, if we take a look at D here, what we're trying to find is inverse sine of 3 over 2. So when we rewrite this as sine of theta equals 3 over 2, and then we look for 3 over 2 in this range here, it doesn't exist. This is not valid because that x does not fall into that interval between negative 1 and positive 1. Now we're taking a look at that final trigonometric function, the definition of inverse tangent function. The inverse tangent function is a bit unique. The inverse tangent function is still denoted as that inverse tangent of x is the inverse of the restricted tangent function where y is equal to tangent of x, where it's greater than, not equal to, this negative pi over 2 and less than, not equal to, that pi over 2. For this restricted area, we cannot include these two end caps here because there's a vertical asymptote at tangent of x at those locations. So we have a discontinuity at the end caps of this domain. When we want to look at y, where y is between that negative pi over 2 and positive pi over 2, and x is any real number. There's no restriction for x when it comes to tangent. The function for graph in the figure 7 has that domain restricted. In figure 8, to create this 1-to-1 ratio for this inverse tangent function here. Notice that our tangent function is already restricted as it's graphed. When we find the inverse of the tangent function, our range is still restricted, but our domain, the x values, are not. So when we want to try and find these values here for the table of tangent, what we want to try and find isn't any coordinate point. Rather, we want to try and find the ratio of sine divided by cosine. We found all of those slopes there for tangent in that 3.8 lesson before, where we're really just finding the slope of that terminal ray going from the center of the unit circle to that P point around the circumference. With this table here, we're now able to solve out these 4 problems for inverse tangent. And again, for that first problem A, we're just setting that right away to theta, and then we're going to rewrite that as tangent of theta equals 1, and then we just search to see when tangent of theta equals 1. So we know that theta is going to equal to pi over 4. Notice that for the rest of these functions here, we can find any inverse tangent function by just setting it equal to theta. We then rewrite that tangent function as tangent of theta is equal to that interior, that argument of inverse tangent. For b, we find when it's going to be equal to negative root 3. So we know our theta is just going to equal to negative pi over 3. For part c, we just find when our tangent of theta is equal to 0, and it's just equal to 0 at 0. So that's a nice little solve there. And then finally for part d, we just find when tangent of theta is equivalent to positive root 3 over 3, where theta is just equivalent to pi over 6. Now, we want to start using our calculators to evaluate these inverse trigonometric functions. Calculators will approximate the values of inverse trigonometric functions. You will use that key marked as inverse sine or inverse cosine and inverse tangent above those function keys on our TI-84. These are that secondary key. Be sure to check your calculator manually for how to access these functions. It is also vital that your calculator is placed in radians mode. To solve out example 7 here, what we want to try and bring up is our TI-84 calculators. For our TI-84 calculators, all we really want to try and do is take this inverse sine, plugging it in to our calculator here by simply hitting second and that sine function here as inverse sine. And we just plug in that 1 divided by 4, hit enter, and we get that exact decimal of 0.2526. However, I want to double check first that I'm in radians to make sure that your answer here is exactly the same as on your calculator as it is on mine. First check by selecting mode on your calculator and tabbing down to where radians is highlighted. When we're plugging in these values here, it's going to be in terms of radians, not degrees. So for that first problem A, we're able to say that inverse sine of 1/4 is equivalent to 0.253. Those 3 decimal places for example 7. For part B, we're just using inverse cosine of negative 3/5. So we just go right under here, second to quit, hitting second, hitting cosine now, and now I'm just typing in that value of negative, making sure to use that negative down here, 3 divided by 5. And we find that our cosine function is equivalent to 2.214. We can do that same exact process again for a tangent, or that inverse tangent. You're just selecting second in that tangent option. But I want you to notice that for part D, we're trying to find the inverse cosine of 1.5. Let's see what happens to our calculators when we try this. We know that 1.5 is outside of that range. So if I select second cosine and plug in 1.5, theoretically, the calculator should say does not exist or invalid and give me an error. It tells me that there is a domain error. So I can state that for my answer here for part D, that this does not exist because x is greater than 1. Inverse sine and inverse cosine theta only exist on the unit circle when x is between -1 and +1. Thank you very much for joining me on these 7 examples today, where we explored those approximations of inverse sine, cosine, and tangent, and then we used our calculators to solve them out exactly using those decimals. I hope you guys enjoyed, and thank you very much. I can't wait to see you guys in class. Take care.